Hey children. So today just a little short video for you. We're not going to jump into the next unit quite yet. Just a little note about what's going on with life here. We are getting pretty close to being near the end of the course. Now I say that, but in reality we have two more major units and they're both trigonometry. We're done with logarithms for now. I'm not going to give you a unit test on that. I think for the most part, the assignments we've been doing has given you some practice and given me some evidence of you knowing your stuff. And in general, during this COVID time, I'm going to most likely not be giving a whole bunch of tests. I will be giving a final exam, and that will be probably something I deal with some students individually. Like I may wind up having you answer some questions directly in front of me or that sort of thing, because I do know, of course, everyone is collaborating on these assignments, and that's not even necessarily a bad thing, but at some point I got to make sure that people know what they know and not just know what their smartest friend knows. So more on that, but for now we're going to be saying goodbye to logarithms, and we're going to be looking at trigonometry, and I'll keep everyone posted on that idea of a final assessment. And we'll be deciding on that a little bit more as June progresses. And we may even wind up going back to school for some tiny bits, but we'll see. That's totally up in the air if you've been following the news. You know, nothing is certain. And if anyone tells you anything is certain, like a specific date we're going back, they are lying, because nothing is fully known. There's a small chance some of us might be going back for some parts, but that's still totally being worked out. So anyway, once I know, I'll definitely let people know. Anyway, so just with trigonometry, what I've done here is I've come up, well, I haven't come up with this, but I've stolen this from the internet. This is a unit circle. What the unit circle is it's a circle with a radius of 1. The word uni, like a unicorn, has one corn, has one horn, so a unit circle is a radius 1 circle. You'd be amazed how long it took me to figure that one out, but that's what unit literally means, 1. So the equation is, of course, x squared plus y squared equals 1. This is not super duper important. What is more important is to look at this and just have a look at what it's showing you. They say a picture's worth 1,000 words. I'd say this picture's probably worth 1,000,000 words. This says so much about trigonometry. It says so much about its relationship to circles. There's triangles here. There's all sorts of good stuff. So I made a little checklist of just some things I wanted to run through as we get moving forward into our new unit. So this is an extension of what you did in pre-calculus 11. Everyone did slightly different things in pre-calc 11, but we all should have learned about the 4 quadrants. So this, of course, is quadrant 1, and this is quadrant 2, and this is quadrant 3, and this is quadrant 4. So that should be something you're familiar with. Not a lot else to say about that, so I'm going to check that one off. When you're looking at this, all these different points here, like here and here and here, these are all points on the unit circle. The length of this arm, which by the way, this is called the terminal arm, if you've forgotten that, this is the terminal arm. This always has a length of 1 because we've got a radius of 1. And what this means here is that we can always construct a triangle, and this is something you would have done in pre-calc 11. You can construct a right-angled triangle here, and you could say that if this is your angle, theta, then sine of theta equals opposite over hypotenuse. Now the nice thing about this is the hypotenuse is always 1. This is why a unit circle is used, so that length of the terminal arm, which is the hypotenuse, is 1, and that simplifies calculations quite a bit. So sine theta is equal to just the opposite in this case. But the opposite side is this, which is the value of y. So sine as the y value here, what we can do is we can see that the coordinates of this point with that corresponds to a 30-degree angle actually just has a y value of 1/2. Now you can memorize these points or you can figure them all out. We'll talk about the special triangles and all that in just a sec. But I just really wanted to emphasize that if you ever want to know sine of, let's say, 30 degrees, it's equal to 1/2 because that's the y coordinate. Sine of 45 degrees would be equal to 1 over root 2, and sine of 60 degrees would be root 3 over 2. There's even something a little more fun, a nice little pattern. If you actually rewrite these, you can actually rewrite this as root 1 over 2. This could actually be written as root 2 over 2, and this could be, well, kept the same as root 3 over 2. And even more fun, you can get to this guy, the 90 degrees, which is a y value of 1. You could even write that as root 4 over 2, because root 4 over 2 is 1. So there's a nice little pattern here. As you're going through the special angles, 30, 45, 60, 90, you go root 1, root 2, root 3, root 4 over 2. And this even extends to 0 if you want, because this is root 0 over 2. So that's pretty nifty. Cosine is actually just the opposite. It's the x value. So as we go through the values of cosine here, we can see that if you made a special triangle, I said special, I meant to say right angle, but this actually is a special triangle, then we can see that cosine of theta equals adjacent over hypotenuse. And since the hypotenuse is 1, then it's just equal to the adjacent, which is the x value. So if I want to know cosine of 30, well, cosine of 30 is root 3 over 2. Cosine of 45 is 1 over root 2. And same over here. And what you can actually see is the values of cosine do the exact opposite of sine. It starts at 1 or root 4 over 2, then it goes to root 3 over 2, then it goes to root 2 over 2, root 1 over 2, and then finally root 0 over 2. So that's pretty nifty. I really like when math comes up with these nice little patterns here. It's just so satisfying. So cosine is the x value and sine is the y value, and they have a nice little pattern there, so that's pretty cool. ASTC, that stands for All Students Take Calculus. Hopefully if you're taking this course, you're intending to take calculus, because this is pre-calculus. But what it actually means in terms of math here is all the trig ratios in quadrant 1, all the trig ratios are positive. So we can go sine, we can go cosine, and we can go tan. And if you work out, you'll see all the sine values, they're the y values. Those are all positive quantities. The cosines, all the x, those are all positive quantities. Tan, it turns out tan of theta is actually sine divided by cosine. You may or may not know that, but it turns out that is a true situation. If you would like a very quick proof, it's very easy. Tan is opposite over adjacent. Sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. Do the math and simplify, you'll see the hypotenuses cancel out, and you're left with opposite over adjacent, which is tan. And if you take a positive quantity and divide it by a positive quantity, you're going to get a positive quantity. So what we have is we've got, in quadrant 1, all the trig ratios are positive. In quadrant 2, the S in ASTC, so here's S, T, and C goes like this. So all the trig ratios are positive. Here only sine is positive. The y values are all positive because it's above the x-axis. But the x values are all negative. So cosine's negative, and therefore tan is also negative, because positive over negative is negative. And then the pattern continues. Only tan is positive here. You can see that the x and y values are both negative, so sine and cosine are both negative. But a negative divided by a negative is a positive, so tan is positive in quadrant 3, and then cosine is quadrant 4 for very similar reasons. So what that means is that if you go cosine of 315 degrees, I don't necessarily know what that number is off the top of my head, although I could easily just look over, but I can tell you it's guaranteed to be positive because it's in quadrant 4. And if you are wondering what the actual value is, it's the x value, so it's positive 1 over root 2. Super. Okay, so special angles and triangles. What's all this about? Just remember, there are 2 special triangles you must know and you must have memorized. Now, the way I present these usually is I say the shortest side is 1. The hypotenuse here is 2, and then this horizontal part is root 3, and then this is a 30-degree angle, and this is a 60-degree angle. There's also one more triangle. It's really simple. It's the 45-45 triangle, where you've got the shortest sides are 1, and then this is root 2. Okay, so this is used because we can easily say, well, if I want to know cosine of 30, if I have this triangle memorized, it's adjacent over hypotenuse, so it's equal to exactly root 3 over 2. So these special triangles can allow us to figure out some of these nice angles. We've got 30, we've got 45, and we've got 60. I can't use these to figure out something like cos of 15, although we will find later on, if you know enough identities, you might be able to do that using cosine of 30. Now, so how does this connect over here? There's one simple difference here. I can draw that special triangle in like this, except you'll notice this side is equal to a half, and this side is root 3 over 2, and the hypotenuse is length of 1. So in order to go from this to this, we just divide everything by 2. So instead of saying the hypotenuse is 2, we say it's 1 instead of 1/2. Or sorry, instead of 1, we say it's 1/2, and instead of this, we say it's root 3 over 2. Same thing goes over here. We'll say this is a half, this is a half, and then we actually make this root 2 over 2. So anyway, those are the special triangles. That should not be news to you that they exist. Just make sure you've got them memorized. And you can use 1 over 2, and root 3 over 2, or you can use the full values. I feel like the unit circle is like special triangle light, where they cut 50% of the fat or 50% of the flavor. I've always been a big fan of not having fractions, so I like 1, 1, root 2, and then 1, root 3, and 2. Anyway, it doesn't really matter, just as long as you know that the special triangles exist, you have them memorized. You do need them memorized, and you can also use them to figure out some values. So I'm just going to erase this because I really prefer it in its, what I would call its original form. Okay, so memorize those. If they're not already memorized, get them in there. Okay, and the final last thing here is if you're looking at this unit circle, you'll notice, of course, we've got like 0 degrees and 30 and 45 and 60 and 90 and so on. But we have pi divided by 6, pi divided by 4, pi divided by 3, pi divided by 2. So what the heck does pi have to do with all of this? This is one of the big jumps from grade 11 to grade 12, and we're going to learn a lot more about this in the next lesson. But I just want to give you a little bit of a teaser, I guess. You'll notice that this triangle has a radius of 1. So when we calculate the circumference of this entire triangle, we calculate the circumference as 2 pi times the radius. Now, if the radius of the circle is 1, that means the circumference is exactly 2 pi. And you'll notice that 360 degrees corresponds with 2 pi. So this is a little bit of a funny thing, because what we're used to is circumference is a length, and we're saying the length all the way around the perimeter of the circle, or the circumference, is 2 pi. But we can also say there's an angle of 2 pi. So to go from here and spin all the way around, we can think of this as an angle through which this terminal arm rotates, and it rotates an angle of 2 pi. So 2 pi is interesting in the fact that it can reference the circumference of the circle, but it can also reference the angle. So we say it's 2 pi, and we say 2 pi radians. So radians are a measure of the angle, and they're 2 pi radians in one circle. The difference between the 2 pi for radians and the 2 pi for length is if I make my circle bigger or smaller, obviously the circumference is going to change, but this is independent of the size of the circle. If I have a teeny weeny little circle, the circumference is going to be much less than 2 pi, but the radians inside spinning all the way around, still 2 pi radians, okay, because the degrees in a circle is 360 degrees all the time. And you can even make another comparison where you can then say, okay, well, we have a direct comparison between radians and degrees, where 360 degrees is equal to 2 pi radians, or 180 degrees equals pi. If you're wondering why we're bothering to do this, degrees work just fine. Why go to something else? There's some reasons for this. The biggest difference, I would say, is that when you do things in pi radians versus 180 degrees, you actually ditch that degree symbol. And that doesn't sound like a big deal, but for doing mathematical calculations, it actually is a humongous deal. It's like in physics or chemistry or any other subject where you've got units. If you want to convert 100 centimeters into meters, you have to do this sort of a unit analysis thing where you've got to do this and you multiply it by 100 centimeters per meter. And then you've got to cross out units, and if you want to go do calculations with degrees, you're going to have to deal with those units somehow, and it's actually quite a big pain. So one of the main reasons we get rid of degrees and we're moving on to radians is for the lack of a unit, but there's also a whole lot of other reasons. Okay, so anyway, that's a rough idea of what pi has to do with this. For now, I'm going to leave it there, and I'm going to leave you with the following piece of homework. If you don't know those special triangles, get them absolutely memorized, and you'd even be well advised to sort of, not totally memorize, but be able to recreate and understand this unit circle here. Okay, so that's it, and we'll be starting with the formal official lessons for trig coming up tomorrow. Get yourself caught up if you're not all caught up. Ta-ta for now.